Okay, perfect. Ladies and gentlemen, GCU-ACM Student Chapter welcomes you all to our virtual ACM Distinguished Speaker Talk titled The Power of Big Data. More and more data is being generated around us by every activity in our daily life. Such large amounts of data are changing the way in which we do things and are used by companies and organizations to make data driven decisions. From mobile phones, wearable devices, up to the shopping we do, more and more data is being stored and analyzed for a number of commercial and humanitarian purposes. In this talk, the guest speaker will present big data dimensions and examples of large data processing infrastructures that companies such as Facebook and Google currently use. The speaker will then talk about the way big data is changing our lives, including, for example, how advertisement is being personalized based on our individual data and how working patterns are today decided by data and algorithms. Finally, the guest speaker will present his big data research, where he investigates novel ways to provide access to information on the web by integrating structured and unstructured content together using human in the loop artificial intelligence methods. The speaker for this talk is going to be Dr. Gianluca Demartini, an associate professor in data science at the University of Queensland, Australia. Dr. Gianluca Demartini is an associate professor in data science at the University of Queensland, Australia. His main research interests include information retrieval, semantic web, and human computation. His research is currently funded by the Australian Research Council, the Swiss National Science Foundation, Facebook, and Google. He received Best Paper Awards at the AAAI Conference on Human Computation and Crowdsourcing in 2018. At the European Conference on Information Retrieval in 2016 and 2020. He has published more than 150 peer-reviewed scientific publications, including papers at major venues such as the WebConf, ACM SIGIR, VLDBJ, ISWC, and ACM CHI. He's an ACM senior member, ACM distinguished speaker, and TEDx speaker. Without any further delay and with great pleasure, allow me to invite Dr. Gianluca Demartini. Thank you.
It's going to happen today. Okay, so good afternoon again, everyone, and thanks a lot for the kind introduction. Thanks a lot to the ACM Student Chapter for organizing the event today. Today I'm going to talk about big data. And more specifically, in the first part, I will give you an overview of the type of technology which is being used by different organizations to deal with big data challenges. And then in the second part of the talk, I will give you some examples of the research we are doing here at the University of Queensland with my research group around big data challenges. So just a bit of background about myself and how I arrived to work on big data. So I studied in Italy, where I got my bachelor and master degree in computer science.
Dr. Gianluca, sir,
sure.
We cannot see you. Can you turn on your camera?
Sure, no problem.
If you're comfortable with it, of course.
Yeah, no problem.
Yeah.
Okay, so as I was saying, I graduated in computer science in Italy, and then I did my PhD also in computer science in Germany, where I started to work on information retrieval. And this is really the problem of building search engines like Google that work at web scale. So really systems that index billions of documents on the web that are continuously changing, but then are able to answer queries from users in milliseconds. So that's really where I first started to look at the problem of big data, of managing very large amounts of data and being able to work on them in real time. After that, I moved to the UK, and I spent some time in Switzerland and in US before moving to Australia. And during this time, I had the opportunity to see different contexts in which big data was used, and also the interdisciplinary aspects of big data that we will talk about today. Okay, before we start really going into the details of big data, let me also thank ACM for supporting this series of events under the Distinguished Speakers Program. As you probably know already, ACM is an organization that supports computing professionals and students around the world. So it's really looking at creating links between academics and students and the industry sector around computing. And as you know, today's event is organized by the ACM student chapter, so they are also part of the bigger ACM family. Okay, so let's start to talk about big data. As you probably have heard already, a common way to define big data is by using these V's. And the three most popular dimensions of big data are volume, variety, and velocity. So volume among the three is probably the most popular one, right? When we think big data, we really think about the massive size that data may have, right? And here you can think of terabytes, petabytes, exabytes of data that we need to manage. So that's really the first thing that comes to our mind. But big data is also more than that. Another challenge in big data is that of variety. We often need to work with data in different formats. Imagine social media, which is text, images, videos, reaction. Some data is structured, some data is unstructured. And typically we want to work with all this data in combination. So one challenge is how to do data integration and connect all these different data types together. And the third most common dimension of big data is that of velocity, where it's not just about the size of the data, but it is really about how quickly the data can be generated. Again, social media platforms, they see that very many users generate content continuously. So the platform is receiving content, which can be pictures or short videos like TikTok. And the velocity, the speed at which this content arrives to the platform is challenging for most of the common platforms. So to deal with these challenges, we'll see today that the new computer architectures and algorithms have been proposed, because what was traditionally available really couldn't scale to large volumes and high velocity of data. So let me give you some numbers just to clarify what we mean by very large or very fast. For example, Facebook is processing in the order of petabytes of data every day. And this is, again, probably in the order of hundreds of thousands of iPhones worth of storage every day, every single day. And of course, these numbers are not static, right? Every day it's a bit more. It's only getting more challenging as we go on. And look, it's not only Google or Facebook that have these problems, because more and more across industry sectors, organizations, companies like banks or governments or shopping chains, they also keep collecting this data, and they need to process it in order to make data-driven decisions. So first of all, it's a significant problem. It's widespread across industry sectors, and we will see that to solve it, we will need a lot of computers. Okay, and thinking about the velocity problem, the most common example is Twitter, which has, again, over time, an increasing number of tweets per second being published on their platform. So probably today we are talking in the hundreds of thousands of tweets per second generated by their users. So Twitter has to build a computing platform that is able to process, analyze, store, and manage hundreds of thousands of pieces of content every second. And not only the data arrives at high pace to the platform, but also over time, the amount of content arriving changes. So imagine a very popular users of the platform, an influencer, post some content, a lot of other users will then react to that, and there is a spike in content being generated. So the computing platform that we need to design has to not only deal with the average load over time, but has to be ready to deal with whatever maximum peak of content is arriving to the platform. And again, like for the volume dimension, velocity is not just something that social media platforms need to deal with. Imagine other scenarios where data is coming very fast, a stock exchange market where a lot of transactions happen every second, but also think about the Internet of Things, where you have a lot of sensors in smart cities or in a nuclear power plant, which is continuously monitoring different elements of the platform or the city. And all this data from the sensors is being sent centrally to a computing infrastructure that in real time has to detect an issue, right? If there is an issue in a nuclear power plant, the system has to shut down or act immediately. We cannot really wait any time, otherwise the power plant could explode. So it's really critical that all this data arrives in real time and it is analyzed in real time. And the amount of data, again, will be very fast in these examples. Okay, we've seen a couple of examples about big data challenges, right? And what I want to stress is that it is really everywhere. It's not just the internet companies. The internet companies had these problems first, and that's why they developed most of the solutions. But today the problem is very widespread. Any big organization has a big data challenge, and they end up using the same solutions, the same systems that these internet companies have developed and are using. So let's look at these, how these systems, computing systems work, how they deal with big data. There are really two ways. If our data is growing or the velocity is increasing, there are two ways we can deal with that. So we definitely need to increase the power of our computers, right? And one way we can do it is scaling up. We have a computer, the data just keeps growing, it's coming even faster to this computer. So what we do, we increase the power of this computer, we increase the disk capacity, the memory, the processing power. We just make our computer more powerful and stronger. And that's scaling up our computing infrastructure. The issue with that is that at some point, we really have to stop. We cannot keep having a bigger disk or adding more memory or having a more powerful processor. The problem is that the rate at which the data grows is much faster than the capacity, the power of individual computers. So what people thought as an alternative solution is that of scaling out the computing infrastructure. So rather than using one very powerful computer, what we do to deal with big data is to use very many standard computers and make them work together. So what we do is we distribute our data over these computers, and then we do our analytics, our computations over these computers. And the beauty of scaling out is that as the data keeps growing or becoming faster, we just add more computers to this, what we call a cluster, which is an interconnected set of computers. We just add more, so the overall system becomes more powerful because we can distribute more data over more computers, and we can compute over more data if we have more computers. And then when I say many computers, that's what really I'm talking about. This is a data center, which is a pretty large building. If you can see in the picture, you have a small image of a truck. So the building is this long as compared to the truck, and it is only one data center of probably maybe 50, in the order of 50 to 100 that currently Facebook, which is just one company, has built. And this building inside would look like this. It's this very, very long corridor where you have these cupboards, and within each slot here, you have a computer. And this computer is not necessarily powerful or a mainframe or an extremely expensive server. This one row is probably a $1,000 PC, which is not more powerful than the devices we are currently using. But you see, there is one on top of each other in this rack, and then there is another rack next to it, and this keeps going and going, and this goes on for the entire size of this building. And then we have many of these buildings. So that's exactly what I meant with scaling out. Very many standard computers, and the data is stored over all these different computers, and the processing of the data is done by making these computers work in parallel. So when I say many computers, Google probably today has in the order of more than 1 million of such computers just to power their search engine. And of course, there is more in Google than a search engine, but to power their web search, they have 1 million such computers. And as you can imagine, this uses a lot of electricity. Google itself alone consumes more than 0.01 of the world's energy consumption, which again, in my mind, it's a lot, right? It's just one company, and it's comparable to what the rest of the world is consuming. So it's a lot of electricity. As a disclaimer, Google and the other companies are typically have a net zero carbon footprint already. They consume a lot of electricity, but then they, in a way, do something to compensate for that. For example, they would plant many trees, or they would use renewable energy as a source of energy, but they surely need a lot of energy to power their systems and to power their data centers. When I show the Facebook one, this one is built in Sweden. You see there is a lot of snow around it, and it's built here because these computers will generate a lot of heat. So they use the cool water from outside the building to cool the computers inside without using electricity for the cooling part of it. So they try their best. It is still a lot of electricity that goes into these systems. All right, so let me tell you now how the type of systems that Google and Facebook and these companies, but also the banks and the shopping chains and the big organizations use to deal with big data. And really, it all started about 15, 20 years ago, mainly at Google, which was the first company having these data volume issues. So what Google did is they built a system that was solving their own problem. They used it internally. And then at some point, about 15 years ago, they decided to write scientific papers describing the systems they were using. And these are these three fundamental pieces of work I'm showing here on the slide. The first one was the Google file system, which is a distributed file system. So it's basically a way to store data on these very many computers. And all this is making the assumption that the computers are not necessarily powerful. They may easily break. So when you have 1,000 or 1,000,000 computers, you can expect tens or hundreds of them to break every day. So there is the system is designed to be fault tolerant and reliable to machines failing in the overall system. On top of the file system, what they did is they defined Bigtable, which is a structured data storage. Think of a database, which is working again on the same hardware and on top of the file system they previously proposed and built. And then on top of that, they define MapReduce, which is a way to do computation and analytics, data analytics on top of the data stored in these type of architectures. So they really, with these three papers, they have an entire solution from storing very large volumes of data to analyzing very large volumes of data. But at this point, these were just published papers. So really, no one else other than Google could use these systems because the actual systems were internal products at Google. So what happened immediately after these papers were published is that the open source community started to develop systems based on these papers published by Google employees. And on this slide, we have exactly the three analogous systems. As the previous slide, we have a distributed file system, a structured data repository, and then distributed computation implementing the MapReduce framework here. And these three now are open source projects, so anyone can get the source code and can use the systems for free, and they can contribute back to these projects if they want to improve them or if they have some addition to be made of these systems. So at this point, about 10 years ago, these systems have come to a stable version that anyone can use and deploy in production for free. So really all you need is the hardware on which you run this software, but the software in a way has been made available open source, so anyone who has a big data problem can use them exactly in the same way as the Google and the Facebook and these big companies are using them. Okay, so that's really how we deal with big data, right? Scaling out many computers that work in parallel. But the question is, okay, I don't really have a big data problem. I don't have a big organization. Why should I care about these big data challenges, right? Unless I am Google running a web search engine, why should I really care about these systems and these solutions? Well, I claim that it is really an important thing to consider because this data that is being stored in the data centers across the globe is really data about every one of us. The data that is being stored as a value, as a financial and commercial value with which products are being built. So the data is definitely valuable for these companies because it's data about people. It tells them about how we like to do shopping, which things we like, how we like to spend time, which type of content we like. And this can be easily monetized by means of advertisements. So they can customize and personalize advertisements by making use of this data. And when I say data about us, I really mean fitness tracking, the selfies we take, the apps we use, the GPS data that is generated by our mobile phones and navigation systems when we drive, steps we take. So the mobile devices that we keep in our pocket are really data producers like nothing else before. And this data is a clear value for the company that are collecting them. So it's all good as long as Netflix tells us what movie we should watch next, or if we watch something on YouTube, we see nice recommendation on the right side of the next video to watch, or when we scroll to TikTok, we keep getting more engaging content. It's all good when the application is that. But if the application of this data starts to be whether I am eligible to get an health insurance or not, and then if I need and I go to the hospital, I may not be treated properly, then it starts to be an issue. Or if I want to get a car insurance, I need to pay much more because some data has shown that I may be a risky driver. Or if I want to buy a house and I ask a bank for a loan, then I'm told no because some data has classified me as a risky person who will not repay their loans. So when that's the way data is being used, then we are not happy anymore, right? And we want these decisions to be fair and not to take into account certain types of data. But it's really difficult to control because this data is collected, is being stored centrally, and then decisions are made using this data with not much regulation or thinking about it. So that's where I'm saying it's really important that we consider these things because it is happening, right? The good news is that there is some control put in place. For example, our emails that are stored in the cloud cannot be read by other people unless, again, they have access to our inbox. But employees of a company, they cannot physically read the emails of customers, of users of platforms from that company. But still, what happens is that if not people, algorithms do read our emails. And then they use this to decide which advertisement we see online. And that starts to be borderline, right? Some people would find it creepy that when they browse the web, they see an ad about a place where they just received a flight ticket in their email inbox, right? And they see attraction in that place. And that may start to feel a bit creepy, but other people are totally fine with it because, again, they see a value in this recommendation, which are very personalized and customized based on their current interests. Another example in which algorithms are changing the way we do things are ride-sharing or food delivery apps, right? In this type of environments, a rider is being told what to do by their mobile phone, and indeed by an app on their mobile phone. So if you think a ride-sharing driver, the line has no line manager. Who is telling the ride-sharing driver what to do is an app. And that's different than how work used to be, right? when we used to work in a workplace, we had a person who was our manager, and we were reporting to them, and they were telling us what to do, how we were doing, if we were doing good or not. But now it's an app, which, again, it's using data, a lot of data, to make decisions on whether an individual, let's call it employee, is worth doing a job or not, and which job they are doing. So how much money a person is making is now decided by the app and the data used by this app. So again, it's the new normal, right? So it's not it's not science fiction what I'm talking about. It happens every single day that algorithms decide how much money people make and whether they are worth doing a job or not. It's just a question whether we are happy with that or not. And I think that's some food for thought for every one of us to really consider how the world is changing because of data, because of big data, and because of algorithms using this data to make decisions that impact our daily life. Okay. So all this goes under the name of data science, which is an incredibly, it's a field with a lot of interest and a lot of rising interest into it. There is so much need for data scientists around the world, because basically what I said at the beginning, all the companies across industry sectors have been collecting all the data they can, just because they can, just because systems are available to do it. But now they have all this data and they see the value in the data. They want to make data-driven decisions. And to do that, they need a data scientist. So that's really where me and my group and my students are working in at the University of Queensland. They come here, they study data science, and then they go work as data scientists across industry sectors. I have students who work for in the finance sector for banks and insurance companies, students who work for telecommunication companies, but also students who work for cancer research organizations, and they try to make use of data to find a cure to cancer, which is a different type of problem to be solved, right? Data is so widespread and it's used from scientific research to making money, to helping people, that it's really up to a data scientist to decide where to go work and where to have an impact. I always tell my students who ask me, will I find a job and how much money I will make? I tell them, it's not about finding a job, it's about you making a decision on where you want to find a job, because you really have the option to bring impact to any sector you really want. All right, so this concludes my first part, the first part of my talk, which is which was about these big data challenges, solutions to deal with that, and the implications of having big data widespread everywhere and how it is being used to impact our lives. Let me now tell you a bit more in detail of a couple of examples of the research we are doing here at the University of Queensland with my group of PhD students and postdocs in data science. So that's one slide summarizing a bit all the research we have been doing. I will not go into the details of all of these, but I will try to give you a couple of examples of research projects we have been working on during the last years, which are related to big data and show the, again, in my opinion, the interesting applications of big data to mainly the web. So my research background, as I said at the beginning, started in information retrieval, where I looked at how entities such as persons, locations, and organizations can be used as a way to access information online. So it was really about moving away from this keyword search box where you can type anything to really create a web search experience around entities. And I will give you an example about this. So while building these systems, we then started to combine human and machine intelligence together, and we were building these human-in-the-loop systems that really make use of the power of machines to scale out over very large amounts of data, as we've been talking about, but also keeping human intelligence into the loop to make sure that the quality of the processing is as good as possible. So really combining the scalability of machines, but the ability of human intelligence as well. And then when doing this, we looked at how to embed humans in the loop more efficiently, more effectively, and we've been working a lot on these problems. And then more recently, we started to look at applications like how we can deploy these human-in-the-loop systems for problems like conservation or fake news. And I will give you an example of this as well today. Okay. So let me go through a couple of examples of the research we are doing. This is what I meant with entity-centric information access. So a search engine like Google. And what happens today is that if we type the name of an entity, for example, an actor like Tom Cruise in the search box, what we see is not just a list of search results, which we can click and then visit, or some news articles, but we also see this box on the right, which is called Entity Panel, which shows a number of things. It shows some images, it shows a short summary from Wikipedia about this entity, this actor, and some structured data, right? You see it was born on this date, and it is this tall. Apparently, that's a piece of information which is frequently searched for about Tom Cruise and all the wives he has been having over time. So some factual information about this entity. So that's really what I've been working on, and how to surface this information given a query in milliseconds. So the reason why this has been implemented by search engines like Google and others is because people ask for it. Almost half of all the queries received by a search engine are about entities like persons, location, and organizations. And today, most of these search engines show a summary of these entities, like you see here. Again, this is from another search engine, but very similar. Another actor will have a short summary and some factual statement, structured information about this actor, and then some related entities, which in this case are movies, and then you can click on this movie and you start observing other information about related entities. Okay, so about this, let me tell you about a piece of work we have been doing to make this possible. The problem is called entity linking, and the task is really the following. We have a news article like this one. The task we want to solve is that we want to identify every mention of an entity, for in this example, organizations that are mentioned in the text of the news article, and create a link from this piece of text to a database of entities that we call a knowledge graph. And you see, if you are able to do this, if you know that Facebook is this entity in the graph, and then Instagram is this entity in the graph, then we can exploit the structure of the graph to find these related entities, right? Like the movies starring Matt Damon. If we know which node in the graph Matt Damon is, we can then walk through the graph to find all the movies he was starring in, and then present this to the user. So if we are able to have links between documents and these entities, we are creating a graph of entities and documents that will allow us to, again, surface information to users who are searching or browsing content online and tell them, for example, that the CEO of Facebook is Mark Zuckerberg. Okay, so that's the problem. It's called entity linking, and it's really about creating links from documents to a graph or a database of entities. Let me tell you how we build a human-in-the-loop system to solve this problem. That's the system that we designed and implemented. The input are documents like web pages or news articles, and the output is what we have seen before, the same news articles with a link from an entity mentioned in the text to a graph of entities. So let's see how we go from input to output. Given a document, actually we can use just fully algorithmic tools from natural language processing to first identify entity mentions, these red boxes around in the text, and then use another type of algorithms to create this link and really identify, say, Barack Obama mentioned here to the Barack Obama entity in this database of entities. But what we did is, rather than just using this fully machine-based solution, instead of stopping here, what we did is we took the result of the algorithm, and then based on the confidence of the algorithm, we decided whether to ask some people about this entity or not. So what it means is that if the algorithm was not very sure about Apple being the company or being a music band, then we were asking a human to double check this news article and tell us whether Apple is the company or the music band. And we did this to a crowdsourcing platform where we can programmatically send questions or tasks to people and then receive back the answers from these people programmatically through an API. So our piece of code was taking the result of the algorithm, checking the confidence, asking people, getting the answers back. And then rather than just trusting the answers from these people, we wanted to combine the answer from the algorithm and the answer from the crowd together in order to make a final decision. So this component is probabilistic network that gets the algorithmic results and the human results and blends them together is the most interesting bit of this architecture. So let me spend a minute to go through this step, which is again how we combine algorithmic results with human decisions. So that's our probabilistic network. What we have here at the bottom are the the algorithmic results, or these black boxes are the confidence scores, the probability of an entity being the correct one. So if our mention is Apple, L1 would be the company based in Cupertino, California, L2 would be a fruit, and L3 would be a music band. And each of three possibilities would have attached to it a prior probability of this being correct coming from the algorithm. So if the algorithm is sure that it's Apple the company, then we stop and we trust the algorithm. But if it's not very sure and the probability of each of the three options is almost equal, then we go ask some people. And these W1, W2 are our crowd workers, or people who tell us what they think the correct entity is. And these workers also have a prior probability. So we might know that W1 is very good, so we want to trust W1 more than W2, who maybe is just a new worker with not much experience, so we give it a lower probability of being right. If you don't know anything about these two, we just give them a 0.5 to each of them. Okay, and that's basically it. We have the algorithm at the bottom. We have people, humans at the top, and then we just combine these things together. So the workers will tell us what they think. These are their decisions. So every possible combination between the options and our workers are displayed here. So for example, worker 2 will tell us what they think about the entity number 3, and so on and so forth. So we set these to observe variables, and that's basically it. We can run probabilistic inference, and then we will have a posterior probability of these L1, L2, and L3, which will tell us what the algorithm and the humans together think about which is the correct one. And that's what we then take as an output of the system, right? Once we know the probability of these L1, L2, L3, this will then become the output of the system, and then our final links are generated. So we can do this purely machine-based, or using humans in the loop, combining the answers and then generating an output, a decision for the links as well. We did a bunch of experiments, and when we observed this, that it works better. No surprise. When you involve humans in the loop, you improve significantly over the machine-based solution just by itself. So if you use humans, you do better, but also if you combine them together, the algorithm and the humans, you do even better, right? So this is the improvement over having humans in the loop using crowdsourcing. But if you combine humans and algorithm, you do even better than just humans. Okay, so that was just one example where the idea is really to build these hybrid human-machine systems, or human-in-the-loop systems, where the trade-off or the best combination is to do the machines make the hard work, the scaling out over large amounts of data, as we have been talking about, and then asking the humans selectively to contribute in a way they can improve the quality of the output, basically. And there are different ways you can involve these humans in the loop. For example, you can ask them to pre-process data. Machine learning is a typical example of this. You have humans manually label pictures of cats and dogs, telling you this is a cat, this is a dog, and then you train a machine which will learn from the examples to distinguish between cats and dogs in images. So here the humans are pre-processing data so that the machine then can scale up the same task. And post-processing is the example we have just seen. First, we run an algorithm. We let the algorithm and the machine process all the 100 billion documents we may have, and then selectively we ask humans to double check only the cases where the algorithm is not confident. All right, so that's the idea of human-in-the-loop systems. So what we learned from this work, from building these human-in-the-loop systems, is that it really works, right? If we involve humans, we can get a better quality results. On the other hand, once you start to have humans in a computational system, it becomes tricky because humans are not machines. And they are not deterministic, they are not predictable, so many different things could happen. For example, different workers, members of the crowd, would perform differently. So it really depends who is doing the task, and the output would change. Also, some are of good quality, some are low quality. It's very hard to predict how long it will take for people to do a task, while machines are very fast, as we know, but people are not that fast in processing content. So there is a number of challenges that arise when you have humans in the loop. And we have been working on these challenges, as I mentioned earlier. I'll give you one example on how to find the right member of the crowd for a given task. And this goes back to using data to understand people, as I mentioned before. So what we did is fairly simple and not very surprising. We built a Facebook app some time ago, and we were asking people on Facebook to complete tasks. Specifically, we were asking to annotate images or to answer questions. And then we were trying to understand who is good in doing a certain task. So our tasks were, for example, I show you a picture of a football player and you need to tell me who they are. Or I ask you a question about cricket and then you need to answer the question. And as you may imagine, some people are very passionate about cricket and some people, they never heard about cricket. So depending on the person you ask, you will get a very high quality answer or a completely wrong answer. So in the experiments we ran, we observed that if people like many relevant pages on Facebook, which are relevant to the task they are doing, so if they follow many cricket teams and cricket players and read a lot of news about cricket, they will be very good in answering questions about cricket. So that's what we see in this plot. On the x-axis, you have these relevant likes, how many things they like on Facebook, which is relevant to the task, and then the quality of the work they do on the task. So what we see here is that if they don't like anything relevant, they could still be very good or they could be very bad. But as long as we start to see some relevant likes, you see that the quality tends to be good, right? We don't have low quality answers from people who have a lot of interest in the topic. So that was the trick for us, right? If the contributor, if the annotator, if we have data about showing that they are interested in the task they are doing, then we know the quality will be very high. And this, again, it's another example of using data about people to understand them and then to give them recommendations, in this case, of the type of work they could be doing and could be doing well. Okay, so after this, we kept working on collecting and using data to understand how people interact with information. For example, we have been asking people to do annotations, to label data, to then train machine learning models. And we have been, in a way, observing them doing these annotation tasks by collecting data, all the clicks they do, all the keystrokes on the keyboards, all the mouse movements, whether they change their mind after they create a label. So we have been collecting all these labels to really understand how people complete these tasks and how they make decisions that are then used to train a machine learning model, right? It's this pre-processing human-in-the-loop approach I've mentioned. Okay, I'll give you one interesting example, which is that of fake news. We have been asking human annotators to label fake news to generate a training data set for machine learning to then classify and identify fake news by itself. As you can imagine, this is a timely problem that many organizations are trying to solve, especially social media. There has been a deluge of fake news on social media, and these companies want automated systems to detect fake news automatically. So what we did is we observed how normal users can label fake news. So what we did is we asked about 600 people online from the US to annotate, to look at statements like this and tell us whether that statement is true or not. We also showed them that this statement was made by a politician from the US. And what we have, but we didn't show to these people, is what the journalists, expert fact checkers, labeled this statement. So this statement was labeled by an expert journalist as mostly true. But the people were just seeing the statement and they had to tell us whether they think it's true or not. So here our research question was really to understand whether non-experts, average web users, are able to identify fake news by themselves or not, as compared to experts, to journalists. And that's what, again, fact checkers do on a daily basis. They try to identify the sources and the data to then attach a label on a statement, whether that's true or false. Okay, we did this experiment, and the good news is that it actually works. It's possible. What we see here on the x-axis are the expert labels on 6 levels. So 0 here is completely fake news, and 5 is completely true, and the levels in between are something in the middle between true or false. So 4 is almost completely true, 1 is almost completely false, and so on. And on the y-axis, you have what our participants said, the average web user, what they said about the statements. Again, experts here and non-experts here. And what you see in the plot is that there is a trend, right, going up. So you get the lowest on the left, and then it goes up to the right. So the higher the experts, also the higher the non-experts said. On the other hand, if you look at a single dot, there are many critical mistakes, right? This blue dot is a non-expert saying that this statement, which is completely false, is pretty much true. So that's an issue, right? If you look at the single individual, it can go very wrong. But if you look at this crowd of individuals together, if you combine them, if you use this wisdom of the crowd, there is a trend correlating with the expert judgments. So that's the good news. If we ask enough people, even if they are non-experts, they can match what experts have been saying about the truthfulness of these statements. But now if we break down into these little dots and try to understand why some people get it wrong, then it becomes pretty interesting. This is the same plot as before, but now we break these dots and we color them as blue or red based on their political background. So let me tell you what this plot is about. Like before, on the x-axis, we have expert labels, and on the y-axis, we have non-expert labels. In this plot, we see statements by Republican politicians, and we see here the red dots are non-experts who have a Republican background. So they voted Republican at the last election. And you see at every single level of truthfulness, from the true to the completely false, the red dots are always higher than the blue dots. So this means that Republican voters tend to believe to Republican politicians significantly more than average or than anyone else. And this is true when the statement is actually true, but also when the statement is completely false. So this means, this is also true if you swap the colors, right? It means if a statement is aligned with my political beliefs, I'm going to believe to it even if it's false, which is not surprising, but it's a bit scary, right? It means we are prone to this risk of falling for fake news because it reinforces our beliefs, our thinking. It is aligned with what we already believe to. So it's only reinforcing our possibly wrong beliefs. Again, this is a result of an experiment we did. It's not a surprising result, I must say, but again, something to think about. All right. So in summary, we have been talking about big data and about these human-in-the-loop systems, which really combine the ability of machines to scale out and deal with very, very large amounts of data through this interconnected cluster of commodity machines, and together the quality of human intelligence to understand content and to manually annotate and curate content. When we do this, we need to deal with challenges from humans, like that of bias. We've seen the political bias example in the fake news scenario. So all this, when we have human annotators, they have their own bias, and their bias will be reflected in the data they annotate. We have seen it in the fake news example. And the problem starts when we start to train artificial intelligence models with this biased data. What the result will be is that the AI we train will have the same bias, and the output, the decisions made by this artificial intelligence will also be biased. So we are carrying on bias and stereotypes from the data, which has been labeled by humans at the first step. All right, so I'll stop here, and thank you for your attention, and I'm happy to have a discussion and answer any question you may have. Thanks.
Thank you very much for your insightful discussion. It was great having you with us. My question is, you are combining the human perspective with the artificial intelligence. So results are again not very good. So what is going to happen in the future? What you are looking at, how we're gonna form a system which can really predict the right or differentiate between right news and the fake news? I think the problem is very critical, and how are we going to solve it?
Yeah, I agree. Thanks for the question. It's a very critical problem. Artificial intelligence is being used more and more everywhere. It's embedded in our devices. It's coming into our homes, in our workplace. So it's widespread. So I agree. It's an important problem to look at. I believe that in the future, the research community will be able to deal with these challenges by proposing solutions that take into account all these requirements of fairness, of ethical decision making, of taking into account bias. Look, in the end, even when we didn't have artificial intelligence, when people were making decisions, this bias was there, right? It's coming from people in the end. When people were applying for jobs and there was an employer, a human employer deciding, there was still unfair decisions being made, right? Some people could hire someone because he's a friend of a friend, or because they had a recommendation, not necessarily because he's the best candidate. So I don't think without AI we are any better, but AI gives us the opportunity to fix these problems, right? We cannot just let AI reflect all the problems that were there before, but we can tweak it to make the decision that AI makes more fair and more balanced, more ethical. I think it's not a solved problem. It's still something that we need to work on. And we need a diversity of human beings to work on these problems, right? We really don't want the West Coast of the US, the white male software engineering in California to solve these problems, because that doesn't sound that they are going to solve it in a way that is good for everyone. They are going to solve it in a way that is good for them. So we really want many different people to solve it in different ways so that the result can be as fair and diverse as possible, in my opinion. But we'll see what happens in the future.
So is there any growing opportunity of existing of some kind of institute in the artificial intelligence like Human Rights Commission or Human Rights Watch or Amnesty International, the organization that can keep check on the things that are unbiased, and they can feed in the data, and so we can make better decisions. I think otherwise the biasness could not be eliminated at all altogether.
Yeah, I agree. It's a difficult problem, and it is interdisciplinary, right? It's not just about designing an algorithm. I think I am a computer scientist. I know how to do algorithms and computing systems, but I think we need help from many different aspects. We need help from psychologists and social scientists, but also legislators and how we make processes that are applicable everywhere in the world. I think there is a risk that these US-based few big organizations are monopolizing the way artificial intelligence research is being done, and that comes with a risk. Unfortunately, there is not yet. So the current situation is that there are really 3 or 4 organizations monopolizing the research in artificial intelligence, and that's not good in my opinion. It would be nice. It would be critical that, especially in the public sector, in the NGOs sector, there is something else going on, right? To not compete, but to complement what these internet organizations are doing. It's very difficult to compete with them because they have the critical mass of human resources, computing resources, and data to make this happen. But I think it's very important that there is something outside them trying to also solve these problems. Unfortunately, today it's not the case, right? Today, the research in AI is monopolized by few companies.
So, Professor, I was reading about blockchain technology. Is this a solution to all these, because they're based on the trust and integrity and the things you are talking about that can solve all these issues if we combine blockchain or Web 3.0 with the AI? Is this a solution?
Maybe it could be. I don't think blockchain can solve all the problems that we have, but it can be a building block of the solution that we are looking for. Again, as I said, the solution is probably interdisciplinary. Blockchain is in a way a data structure that allows to decentralize in a way the approach that we can take. I think decentralization is very positive, right? Because of what I just said. Currently, the internet is very centralized, is dominated by these very few platforms, and it's not good, as we have seen in the last few years. Many social issues arise because of that. Blockchain is a way to decentralize and remove the power from a central authority. That's really what blockchain is about. So if you are able to decentralize, you are also allowing more people to contribute to the solution. So in a way, I think it's positive, and it could be potentially part of the solution. I don't think blockchain can solve all the problems, but yeah, I think it's a nice approach to have a decentralized solution, right? You could potentially store data rather than in a data center through a blockchain, and these computers are not all sitting together in a building, but they are our devices, right? And we store our data on our devices. We have control over it. There is encryption and privacy. So that may be a way to go using blockchain.
Thank you, Professor. Another question?
Okay, 001, your mic has been enabled. You can ask your question now.
Sir, I'm going to provide a context then. In the project of AlphaGo and AlphaZero, AlphaGo was provided the data of human competitions, and AlphaZero was uh, learning based upon simulations from scratch. Okay, so AlphaGo defeated the world champion in Go, but AlphaZero defeated AlphaGo with 0 to 100. So my question is that without giving human inputs, simulating the real problem issues based on purely artificial intelligence, can these problems be solved in a much more efficient way?
Very good question. Thanks a lot. Maybe, I think the answer is maybe. Today, reinforcement learning, which is what AlphaZero is using, has been successfully applied to games, mainly to Go, sorry. The game, as we have seen, is very successful. It has been applied to Atari games, which are these very early video games, very simple. But again, reinforcement learning works really, really well for that, where really the algorithm can try many different things until they find what really, the strategy that really works. So today, reinforcement learning is applicable to problems where a solution, a strategy, a sequence of actions has to be found, and then they can again play with themselves until they find the best strategy, and that works very well. It's still not really possible to apply these reinforcement learning methods to any problem. So today, the vast majority of machine learning is still supervised and using human data. Again, there is a lot of investment by these companies on reinforcement learning for other problems, so they can move away from the need of data to train these models. We'll see. I think I'm not very confident that reinforcement learning will be applicable to, say, image classification, because again, there is a need for knowledge, right? If we want to label a video saying what happens in the video automatically, we need the model has to have knowledge about different elements, right? So if we give this knowledge, this common knowledge, common sense knowledge, right? That's what the AI is often missing. If you can give human knowledge and common sense knowledge to these algorithms, and then combine it with reinforcement learning to really become more and more accurate and effective, then I think yes, I think that could be the next breakthrough in artificial intelligence. It will probably take 5 to 10 more years, maybe more 10 years for that to happen, to really have a breakthrough in which reinforcement learning approaches like AlphaZero can be applied to all the AI problems. But I don't think that by itself it will be possible. We need to combine it with human knowledge as well, one way or another. Thanks.
All right, thank you so much, Doctor. I believe we have no more questions. I would now like to invite the Chairperson of Department of Computer Science of GCU Lahore, Professor Dr. Sadraza Kazmi, for concluding remarks.
Thank you very much. Do you hear me? Hello?
Yes, sir. Yes, sir.
Thank you very much. I'm grateful, and good evening, Professor Demartini, and good afternoon from the student from my side and the colleagues. And I'm really grateful for your very comprehensive talk on where you talk about the chronological development of big data, and then there's a colossal development and the day-by-day development in the data and your research activity and implementation, and at last a very interesting experiment you expedited, and for my young minds of young students of my department. So I'm really thankful on the behalf of my university, Government College University, Lahore, Pakistan, and the Department of Computer Science, and especially on the behalf of ACM chapter, student chapter over here, and on my own behalf. And I would humbly request if we could have a kind of collaborative work so that my young student could get benefit from your research work, from your very great work, so that we could have these young minds could work in this big data area. And secondly, if there might be possibility of some kind of MOU so that my young students could really collaborate with you, we can get benefit from your research work and your research activity. I'm really thankful for your time and everything. Thank you very much.
Thank you. Thanks a lot for organizing the event, and sure, let's have a conversation offline about possible collaborations.
Thank you. Thank you. Thank you very much.
All right, Professor. On behalf of GCU-ACM Student Chapter, we thank you for attending, and we are really grateful to you. I think that concludes the session. Thank you.
Thank you. Thanks everyone again for organizing it. Bye-bye.
Thank you.
Goodbye.
Bye. Bye.